Look at the sheer scale of the modern electrical grid. Every light, motor, and server farm on Earth operates on an invisible relationship between electricity and magnetism. For centuries, we treated these as completely separate phenomena. Lightning was one thing, lodestones pointing north were another. In the 1830s, Michael Faraday set out to find a mathematical and physical bridge between these two forces. He started with a logical assumption. If electricity can create magnetism, a magnet should create electricity. But when you place a tremendously powerful magnet perfectly still inside a copper wire coil, absolutely nothing happens. The meter stays at zero. The system stays dead until you physically move the magnet. Drop it through the center of the coil, and electricity suddenly surges through the wire. The mere presence of a magnetic field generates zero power. To induce an electrical current, the universe demands relative motion and change. This diagram visualizes magnetic flux. Flux is the measurable amount of magnetic field lines piercing through a specific surface area. If those field lines remain static, the circuit remains dead. But when you force them to increase or decrease, this graph traces how that rate of change over time induces an electromotive force, or EMF. EMF is the voltage generated by a changing magnetic field that drives current through a circuit. This is Faraday's law of induction. Epsilon is the induced EMF, and d phi b over dt represents exactly how fast the magnetic flux is changing over time. The negative sign at the front represents Lenz's law. It tells us that the coil inherently opposes this change in flux, creating a physical magnetic resistance you can actually feel when pushing a magnet into a loop of wire. Time, the dt at the bottom of the fraction, dictates the output. It's not about how much magnetic flux exists in total. It is entirely about how rapidly you force it to change. There is a practical limitation here. A single loop of wire experiencing a changing flux only produces a fleeting, tiny voltage. The engineering solution is to stack those single loops into a densely wound coil. When we update the math, we add the number of turns, represented by n. This n acts as a direct mathematical multiplier for the total induced EMF. Moving a magnet, moving a coil, or switching a neighboring current on and off might look like completely different physical actions in a laboratory, but they are just different methods of changing the magnetic flux. By manipulating flux and winding enough wire, we can scale up those tiny voltages to engineer massive electrical currents out of thin air. We can break open that magnetic flux variable to reveal its three internal geometric components. Flux equals the magnetic field B multiplied by area A and the cosine of the angle theta between them. Theta is the angle between the magnetic field vector and the area vector of the coil. Using the first lever, we can force an induced EMF by simply turning the strength of the magnetic field itself up and down. For the second lever, we keep the field constant, but physically crush or expand the size of the wire loop. Changing the surface area forces a change in the total flux. The third lever keeps both the field and the area constant. By simply rotating the loop inside the magnetic field, the angle continuously changes, driving the flux up and down. Faraday's equation offers three distinct physical pathways to generate power. Of the three controls, the rotation dial drives nearly all modern power generation. Massive industrial turbines, whether pushed by coal-heated steam, falling water, or wind, are essentially giant machines built to continuously rotate wire coils inside magnets. The alternating current in our wall outlets runs at 50 or 60 Hertz. Hertz is a unit of frequency that measures cycles per second. This frequency is the direct mathematical echo of those generator coils physically spinning 50 or 60 times every second. Every time we turn on lights, boot up a computer, or charge a phone, we are tapping directly into Faraday's mathematical control panel, converting raw, continuous motion into electrical power.